everyone on today's headlines. So today we will have two presentations and both of them will be very special. So first of all we will have a talk by Ryan Allured, who will present what many of us hope will be the future directions for the next large US X-ray mission, namely SmartX. So this will be a technical talk. After Ryan, we will hear from Reid, who will provide an overview of a major effort to refine the large-scale structure of the galaxy, and he's going to tell us about a VLB observing program, which is the largest ever awarded program. So, Ryan, please.
Okay, thanks. So this is the talk outline. I'm going to start over with a brief overview of adjustable X-ray optics motivation and the overall concepts and implementation. And then the bulk of the talk will be wavefront sensing metrology and some influence function modeling, and then follow up with plans for the future. All right, so this is a slide stolen from Alexi. This is the SmartX overall concept. People are now recently talking about X-ray Surveyor, which is a mission concept study being led by Marshall right now. But essentially, we're looking for angular resolution identical to Chandra, so subarc second angular resolution, effective area. The science instruments would consist of a microcalorimeter for high spectral resolution at higher energies, and then a CMOS active pixel sensor to take advantage of the best angular resolution of the telescope. And then insertable gratings to achieve high spectral resolution at the lower energies. So an enabling technology to make this a reality is adjustable X-ray optics. So the goal again is lightweight optics with subarc second angular resolution with low mass and high packing efficiency to maximize your effective area per unit mass. So the concept is demonstrated by this cartoon over here, where we have a 0.4 millimeter thick Corning Eagle glass substrate. Deposited on the back of that is a continuous platinum ground electrode. And then we have roughly a micron and a half of PZT, or lead zirconate titanate, which is a piezoelectric material that can contract upon the application of voltage. Finally, we have pixelated platinum electrodes on the back. And by wiring those up to exterior electronics and carefully applying voltages, we can control the in-plane strain induced over the surface of the mirror and get it to bend back into the right shape. And this is particularly useful because we can do so even after we've mounted and bonded the mirror, and even in orbit. So current prototypes that we have around the lab consist of 10 centimeter by 10 centimeter glass segments slumped to roughly a 30-degree segment of a Wolter 1 shell with 10 millimeter by 10 millimeter actuator cells. And it's important to note that because the piezo can only contract, you can only make the mirror bend one way for a given cell. So if you look at this cartoon, this would be before and after. Before, after. Okay, so we've done simulations that lend confidence that we can actually do this. What you see right here is distortion data taken from an actual mounted IXO mirror from the 2000s. And essentially an interferometer was used to take axial slices of the figure. These were stitched together into the map that you see here. The color bar scale is in units of microns, so we're looking at a little over a micron and a half of peak to valley distortion data over the surface of the mirror. So then we modeled influence functions with finite element analysis, in other words, we looked at the mirror deformation predicted as a function of strain for each individual cell. All of those were combined with the distortion data into a bounded least squares minimization routine to determine the optimal influence function magnitudes to correct the mirror. And the estimated point spread function goes from an RMS diameter of 14 arc seconds down to 0.4 arc seconds after correction, which is right where we want to be. And nearly all of the actuators require voltages that are equivalent to single cell actuations of between 0.2 and 0.4 microns peak to valley. Okay, so that combined with actually measuring the mirrors moving to this magnitude lead us to believe that we can make this a reality. What you see here is the first cylindrical piezoelectrically adjustable prototype. Again, it's 10 centimeters by 10 centimeters, 0.4 millimeter thick Corning Eagle glass, and you can see the pixelated piezo cells on the back of the mirror. Over here is optical profilometer displacement data for 4 different actuator cells as a function of applied voltage. And you can see that the peak displacements are between 0.5 and 0.7 microns. Okay, so we can move the mirrors to the right magnitude. Of course, actually correcting a mirror depends very strongly on how well you know the influence functions. So before I got here, the optical profilometer was used to scan over the surface of these mirrors and measure influence functions. But the optical profilometer is slow. It took something like an hour to do an entire scan. And so over the course of this measurement, thermal fluctuations can distort the mirror and add systematic error to your measurements. So we would get agreement over the entire mirror surface on the order of 100 to 200 nanometers RMS. So a large part of what I've been working on is developing Shack-Hartman wavefront sensing metrology to improve both the accuracy and speed with which we can measure the mirrors moving. So a brief overview of Shack-Hartman wavefront sensors. Essentially, you have a micro-lenslet array positioned in front of a detector, typically a CCD or a CMOS camera. And each lenslet focuses a spot onto the detector that is tilted based on the local curvature of the wavefront hitting that lenslet. Okay, so by measuring the shifts of all of the spots, you can convert those into wavefront slopes and do a 2D integration and reconstruct the wavefront that hit the lenslet array. All right, so then you can imagine illuminating a deformed optic with a plane wave. The wave reflected off of that optic carries those distortions in its wavefront, and if you can pick those up with the wavefront sensor, you can back out the figure of the optic. Of course, the key to doing this accurately relies on adequate imaging of the deformable optic at the wavefront sensor plane. All right, so this is our initial optical design for a wavefront sensing metrology setup for a flat mirror. And so you have a single mode fiber laser diode that creates an expanding spherical wave, hits a beam splitter, it gets collimated down here by a lens. Then you have a deformable optic positioned after that. The light goes back through the system, hits a field lens, which forms an image of the DM at the wavefront sensor plane. And so the imaging is such that the image wavefront is a scaled version of the wavefront at the object plane. And finally, you have to do all of these measurements in reference mode. So to do figure, you would put an optical flat at this position, measure the wavefront, remove it, put your test optic back in, measure that wavefront, subtract the two, you get your figure. For influence functions, you don't have to switch out the optic. You just put in the DM, measure the wavefront with no voltage, then apply the voltage, measure it again, you have your influence function. All right, so this was first done on this piece right here. It's a 100 millimeter round, 0.4 millimeter thick, piezoelectrically adjustable glass. This particular piece had a 1 micron PZT layer. It has a nickel reflective coating to permit the wavefront sensing metrology and get rid of the back reflection. And it's bonded to a 6-point flexure mount, shown here in aluminum. So then we have conductive epoxy that connect to each of the cells on the back, go up to these connectors here, and then into a computer, which we use to control the voltages on the mirror. The entire setup is shown right here with the collimator and the deformable optic in this corner, and the wavefront sensor, light source, and field lens down on the other side. All right, so this is, where's my pointer? This is a movie of real-time observation of the entire surface of the mirror. So it's 100 millimeters laterally. The vertical scale is in nanometers, and I'm taking 3 individual cells, tying them together, and raising the voltage from 0 to 3 volts over the course of 20 seconds. For a final peak to valley actuation of the 3 peaks of roughly 0.3 microns. And so this demonstrates that we can make these mirrors move quickly and we can measure them accurately. Okay, but how accurately? This is a comparison of the central cell of the mirror to the FEA model, the measurement compared to the FEA model. These are the residuals over the entire surface of the mirror. We're getting 8.7 nanometers RMS agreement, 38 nanometers pizza valley. And the residuals are highly systematic. If you take the Zernike transform of these residuals, 84% of the power ends up in the focus term or the spherical aberration term. And I'll get into why that is in the next slide. This is just a slice through the center where measurement and model are shown in blue and the residuals in red. All right, so what are the sources of error? If you take an optical flat, measure its wavefront, and then keep measuring it with respect to itself, you end up getting roughly 1 to 2 nanometers RMS repeatability over the whole beam. But if you do the same thing with our mirrors mounted on these 6-point flexure mounts, you can actually see the mirror breathing on the mount in short time scales, on the order of tens of seconds. And this is an example of watching the mirror breathe on the mount. You can make out the 6 flexures very clearly, and that accounts for roughly 6 nanometers RMS of the error. And it's primarily in the focus and hexafoil terms of the Zernike polynomials. All right, so I also used ray trace simulations to investigate static errors due to misalignments in an inherent system modulation transfer function. So of all of the potential misalignments with realistic tolerances, the only ones that made any difference were focus error, or an axial misalignment of the field lens or the wavefront sensing camera. And that accounts for roughly 3 nanometers RMS error due to washing out your signal. Okay, so then there's also roughly 2 nanometer pizza valley error due to the inherent modulation transfer function of the system, which is dominated by the lenslet size. Each lenslet is 114 microns square, and that provides a cutoff to the high spatial frequencies that you can measure. And so the remaining residual can be explained by the accuracy of the FEA itself. FEA is not perfect. I hear uncertainties on the order of 5% quoted frequently. So if you take all this into account, we're claiming that the measurement agrees to the model within metrology noise, which we were pretty happy with. Okay, so I've done some modeling with the assumed FEA influence functions to figure out what our correctability is as a function of frequency, spatial frequency. All right, so I take an input sinusoid distortion map along the axial direction, throw that through the least squares optimizer, and I come up with a correction residual, so the residual ripple after applying the piezo voltages. I take the axial PSD or axial Fourier transform before and after, and that's shown here. And you can see that the sinusoidal peak, that power is greatly reduced. There is some introduction of higher frequency ripple due to the periodicity of the cell pattern. But if you take the overall power before and after, look at the ratio and plot that as a function of frequency, you come up with a modulation transfer function shown here, where at low frequencies, we are very well able to correct sinusoidal ripples. And then as we hit the Nyquist frequency of the cell pattern, that starts to drop to 0. All right, so it would be nice to actually measure this in the lab with a real mirror and real metrology. So this morning, actually, we received a high-yield mirror from Penn State University with 5 by 10 millimeter piezo cells. There's only 3 cells that are shorted, and they're off to the edge. So I took this cell pattern, looked at the model influence functions, computed the predicted correction modulation transfer function. The effect of the 3 missing cells is also plotted. It's a negligible effect. And so in the next few weeks, we'll be using the wavefront sensor to confirm this MTF experimentally, which would be a validation of our overall model technique. Okay, so actually also last week, I was able to put together a cylindrical wavefront sensing system. And the idea behind this is that if you have a cylindrical optic, you can transform your plane wave into a cylindrical wave and do the same sort of metrology on a flight-like mirror. Okay, so it turns out that large format aspheric cylindrical lenses are difficult and costly to procure, so we went with a computer-generated hologram instead, which is essentially a phase-etched diffraction grating. And so the concept is shown here, where the plane wave is transmitted as a cylindrical wave that can bounce off your test optic and give you figure data. And so this would be a Zmax test of the imaging capabilities of the system. It's essentially the same sort of system. You have a collimator, a field lens, the addition of the cylindrical null, but then also a cylindrical field lens down here to make sure that the two object planes match up in both axes. All right, so this was set up last Friday. This is the collimator, CGH null, and a 220 millimeter radius of curvature reference mirror. Using this setup, I took a reference wavefront, took out the reference mirror, put in one of our slump samples, and measured the figure. And that's shown right here, hot off the press. It's not a particularly good sample, but it is a demonstration that we can get figure measurements from cylindrical optics. For purely gratuitous reasons, I also took the wavefront of this reference mirror and then referenced it to itself and adjusted the position and made this little movie demonstrating real-time cylindrical metrology. So as I'm adjusting the piston, you get a cylindrical wavefront error as shown here. This scale is in microns. So I'm pushing it in and out, which creates the expected cylindrical deformation. And then I'm adjusting the yaw of the mirror, or rolling it about the optical axis of the system, and that creates a characteristic astigmatism, and it goes in both directions. And these two terms are representative of the figure terms that we are insensitive to. So when you take a figure measurement, you have to put in the reference mirror, swap it out, put in your test optic, but the piston and the yaw won't necessarily be the same, so these two terms have to be subtracted out. Okay, so other future plans. Like I said, we received a mirror this morning. We're going to calibrate the MTF of a high-yield flat mirror. Then we'll be using the cylindrical wavefront sensing system to monitor our slumping progress. We're working on contamination control and improved precision of the post-slumped figure. So the wavefront sensor will be crucial to that. I'll be receiving a high-yield cylindrical mirror, adjustable mirror from Penn State in the coming months. And we'll do the same sort of thing. We'll calibrate a correction modulation transfer function and demonstrate that this technology can correct distortions of the right magnitude. And then in the slightly longer term, our goal is to take an aligned and bonded mirror pair, measure their figure and influence functions, and then use this information for a sub-arc second X-ray test at Marshall Space Flight Center. So that's it.
You mentioned there was 6 nanometers RMS error in the computer early on. Was you mentioned breathing? Was that from thermal effects or what?
So I think it is slow thermal effects, but then I also think it's vibrations. You don't see this with a nice stable optical mount, but you can imagine the mirror flexing back and forth around an unstable equilibrium with this sort of a mount.
Other questions?
So what do we know about how well the piezoelectric material does in space?
So with regards to lifetime?
Yeah.
Okay, so there have been some lifetime studies done. The semiconductor industry has a standard scaling relations for voltage and temperature for how the lifetime should scale. So they've done accelerated tests under increased voltage and increased temperature that indicate a lifetime of 1,000 years or so. So that lended some confidence. So we're doing real-time lifetime tests as we speak, to actually under vacuum and at room temperature. So they haven't failed. They haven't failed yet. And then radiation damage is actually an ongoing study. A grad student at Penn State is starting to look at that right now.
So what would the effect of the cell size on the BeSSeL actuators be ultimately on a real flight mirror?
Okay, so
That builds in characteristic scales.
yeah, it does. Okay, so if you look at, here we go. So it would change the cutoff frequency of this modulation transfer function, essentially. And that has implications to how well you have to slump the mirror at the higher spatial frequencies. If you reduce the size, then you increase the spatial frequencies that you can correct. And so you would be less sensitive to mid-frequency errors at the cost of increasing complexity.
So you said, I think it works this way, the piezo can only shrink the mirror, it can't expand it in any way.
Yep.
Does that force the design of the mirror in some way to be undercurved?
So yeah, I thought the same thing when I came here, but I believe the answer is no. Because of the periodicity of the cells, they introduce a second order print through ripple, and so you want that to be balanced with the residual influence functions from polling the PZT. So if you want those two balanced, and then you're going to want the large scale coding stresses, uniform coding stresses to be balanced as well. So I'm not convinced that we want a negative bias.
Anybody else? If not, let's thank you again.
Thanks.
Doesn't want to come up for some reason.
It took a few seconds for me.
It did, okay. I got the right plug here? This is the right one, right? Yeah. Oh, that came out.
Ah.
Okay, that'll do it. Okay, good. Okay, let's get this going. Let's see. Okay, that looked loud enough? Okay, great. Okay, thank you for inviting me. It's always fun to talk about this stuff. I'm going to basically talk about a very large project that uses a very long baseline array to map the Milky Way, to see what it looks like. And of course, this is what you would see if you go out on a very dark site and had interesting eyes. But what we think the Milky Way, well, before I do that, let me just put up some units that might be of interest. We do radio observations, and I calculated that's about 10 to the minus 7th keV photons. But our count rate is high. In a really narrow spectral line, a single telescope will collect about 50,000 photons per second. And we can do that very high spectral resolution, about 1 million. We can do higher if we wanted, but it's not of much value. Okay, so with that in mind, here's something of what we think the Milky Way might look like. Oh, boy. VPN. I think I'll get rid of Cisco Connect. Okay, let's see what else can come up. Okay, these are two external galaxies that we think the Milky Way might resemble. This galaxy has a pretty nice two-arm spiral and a nice bar across it there. And there's some debate about whether the Milky Way has 2 arms or 4 arms or some other number. This is more like a 4-arm spiral here without much of a bar. And so if you sort of cross these two images, you might get something that would resemble the Milky Way. But the problem is we just don't know what the Milky Way looks like. And that's because, of course, we're inside it. There's dust extinction that basically limits optical photons to a kiloparsec or 2. And so you can't see much of the Milky Way optically. So at radio wavelengths, of course, you can see right through the Milky Way. Dust is not a problem. And here's an all-sky map, or all-galaxy map of the Milky Way in carbon monoxide done by Tom Damon, Pat Thaddeus, and Dap Hartman. And what's plotted here is going along the plane of the Milky Way here. And the vertical axis is not latitude, it's Doppler shift, LSR velocity. And when people did this with atomic hydrogen, and also you can do this with carbon monoxide, you could clearly see that there are arc-like structures in these plots. Here's a white line there. Turns out that's what's called the outer spiral arm in the Milky Way. This red line here, this trail of emission, is the Perseus spiral arm. And of course, it gets pretty complicated in the inner galaxy there. So people could recognize very early on, even in the 1950s, that the Milky Way had spiral structure, and the hope was that you could turn this velocity axis into a distance and make a map of the Milky Way, and then get a plan view and see exactly what it looked like. Turned out that is not very easy. Turning velocity into distance is quite complicated. But here's one attempt using hydrogen to map the Milky Way, done by Levine, Blitz, and Hylas about a decade ago. And so they took all-galaxy map of atomic hydrogen and used kinematic distances to transform velocity to distance. And what you do there basically is very simple. You measure a Doppler shift of a cloud of gas, and you have a model for how the Milky Way rotates, and you just adjust the distance from the sun until the model Doppler shift matches the observed Doppler shift. And you can sort of see some spiral structure in this plot. Jeez. How do you... Okay. If I could get out, I would just turn off the network. Okay. Where was I? So, here's the sun. The galactic center is in here. I'll explain why this is all white in a second. And you can see what looks like a spiral arm out here, and a little piece of one in here. This is actually probably the outer spiral arm in the Milky Way, and this is a piece of the Perseus arm, but it's at the wrong distance, and basically it's about half as far from the sun as that indicated. And the problems with kinematic distances, which make this very difficult to do, are first of all that in the inner galaxy, that's within what's called the solar circle, the same radius from the galactic center as the sun is, one velocity can give you one of 2 distances, and so you have to figure out a way to decide, is it near or far away? If you are looking away from the galactic center or toward the galactic center, a given Doppler shift is usually near 0, and you have almost no sensitivity to distance, and so people usually white that out. Then, of course, you have to assume a galactic rotation model. Usually one assumes circular rotation, and that can lead to errors if that's not true. And then you need a lot of parameters to be fairly accurately known, including the distance to the galactic center, the rotation speed of the galaxy at the sun, theta naught, and you need to know what the sun is doing also, and that turns out to actually be interesting and has caused quite a lot of controversy recently. Let's go back to our 2 galactic pictures here. So obviously we can't do this with kinematic distances. So how do we need to measure real distances to objects to map the Milky Way. So at first thought, you might think that the Hipparcos satellite, which measured parallaxes to 100,000 stars with 1 milliarc-second accuracy, might be able to do it. But if this were the Milky Way, and if the sun were there, that dot is the 10% accuracy circle for distances with Hipparcos. And so you can see it's nowhere near what you need to map the Milky Way. So recently, Europeans launched Gaia, which is sort of Hipparcos on steroids. And the target accuracy for Gaia is roughly 20 micro-arcsecond parallaxes. And that would give you a 10% error circle like that, and you can start doing a large portion of the Milky Way with that. The problem, though, is that Gaia works at optical wavelengths, will not be able to see through the plane, and so they'll be able to do a lot of very interesting work looking out of the plane of the Milky Way, but measuring the spiral structure directly will not really work with Gaia. So here's what we can do now and have been doing using very long baseline interferometry at radio wavelengths. We can get down, we have actually measured parallaxes with an accuracy of 5 micro-arcseconds. It's a pretty small number. And our typical number is closer to the Gaia target of about 20 micro-arcseconds. And so we're working within sort of that circle at 10% accuracy. And of course, we're working at radio waves where we can see right through the plane, so there's no trouble doing things. So basically, if that's the sun and there's a H2 region, a star-forming region here that'll trace spiral structure, and if we have nice targets like masers, which are really bright, fairly point-like objects, we just want to measure that distance by trigonometric parallax and then make a map looking at lots of them. So just one brief slide to show you why we can do roughly 10 or 20 micro-arcsecond parallaxes. So there's the VLBA, the Very Long Baseline Array, that has 10 radio telescopes across the U.S. from St. Croix in the Virgin Islands. There's one up here in New Hampshire, very close to us, and Hawaii around the corner there. And the intrinsic angular resolution of this array is basically the wavelength divided by the separation of the telescopes, and that turns out to be about 250 micro-arcseconds at 1 centimeter wavelength, which is the 10 to the minus 7th electron volts. Okay, if you want to measure the precision, you measure the centroid of something, the precision with which you can do that is roughly half the fringe spacing divided by the signal to noise. And that easily gets you down to 10 micro-arcseconds, even for fairly modest signal to noise values of maybe 10 or 15 to 1. So that's not the problem at all. The problem is always systematics. And here's a street sign in Billerica, not far from where I live, which says West Street, formerly known as North Road. Well, there's a 90-degree systematic error. I'm not quite sure how that happens. Okay. Well, we have to do a lot better than that. And it turns out, and it'll be a long story to explain it all, that in an interferometer, you're trying to control path lengths, optical path lengths between the different elements of the interferometer. We now can do this to about 2 centimeters of path length, of optical path length. And that's about 2 wavelengths at the wavelengths we observe at. So if you make a 2 wavelength error with an interferometer, you basically shift the sky by 2 fringe spacings. And so we will make absolute position errors of about 500 micro-arcseconds based on that. But actually what we do is we use actually a suggestion for measuring parallax that was made by Galileo, that you don't want to try to measure absolute angles, full angles. You want to measure differential angles. And we always measure differential angles between our target in the star-forming region and a background quasar. And we can almost always find a background quasar that's strong enough for us to use within about a degree on the sky of our target. And so 1 degree is something like 2/100ths of a radian, and you basically cancel almost all of your systematic errors by that factor. And so the 500 micro-arcsecond absolute error comes down to about a 10 micro-arcsecond relative error. And that's basically how we can do it. So, about 6 years ago, we proposed a very big project. It's called the BeSSeL survey now. It honors Friedrich Wilhelm Bessel, who measured the first stellar parallax in 1838. And we requested 5,000 hours, or if you like, 20,000 kiloseconds, over about 5 years on the VLBA to try to map a few hundred, get a few hundred parallaxes to high-mass star-forming regions and make a map of the Milky Way over the portion we can see. It's a large group of people who have worked on this over the years. Some come, some go, but some of the major players include Tom Dame here, Carl Menton in Bonn, and Andreas Brunnthaler and lots of other people have done this too. In many, many countries, you can see there. So let me just show you some examples, two examples of parallax data. This is parallax data for some water masers in a giant molecular cloud that is very close to the galactic center. It's about 100 parsecs from the galactic center. It's called Sagittarius B2. And on the left here, what's shown is the position on the sky. So we have north up and east to the left. Scale's fairly small. Major tick marks are 1 milli-arcsecond. And here are the positions starting in, if I can't read it, 2006 over here. And a year later, the source has moved down there, and it's gone along that little path like that. You can see it's not a straight path. That effect is the Earth going around the sun, and you're viewing it from a different point. If you plot, instead of this one, you plot position versus time. And so the blue curve here is the east-west position offsets, and the green ones are the north-south position offsets. You can much more clearly see this bump here. If you then solve for a parallax and a proper motion, you can remove the proper motion, which is the slope here. And if you look at the blue curve up here, you'll see what's left over, which is the effect of the Earth going around the sun. So in September of 2006, the source appeared to be down by a little bit, goes up 6 months later, and comes down again. And so the parallax you get from that is really the amplitude, half amplitude of that sine wave, and that's 129 plus or minus 12 microarcseconds. So this cloud is at 7.8. If you just invert that number in milliarcseconds, actually, you get the distance in kiloparsecs. So this is at 7.8 plus or minus 0.8 kiloparsecs. That's effectively a direct measurement of the galactic center. But as you'll see later, we can do a lot better than that uncertainty with the ensemble of all the sources that we've been mapping. Let me show you one more. This is W49. This is one of the most luminous star-forming regions in the Milky Way. It's a long way away. If we just look at the red curve on this one, I guess I changed colors on you here. This is the east-west offset as a function of time over 1 year, but the scale's pretty small now. From here to here is 100 microarcseconds only. And the amplitude, the half amplitude of that curve again is the parallax, and so the parallax here is 90 plus or minus 7 microarcseconds. This thing's a little past 11 kiloparsecs. It's past the galactic center. It's out on the other side of the Milky Way. Okay, so about a year ago we published our first couple years of data. And here's a plan view of the Milky Way. Here's the galactic center. Here's the sun. So that's about 8 kiloparsecs from here to here. Every dot on here is a high mass star forming region whose distance we've measured by parallax. And there are about 100 of them there. The colors of these dots, they're colored only by these arcs in the carbon monoxide longitude velocity plot. In other words, let's start with the outer arm here. Those sources all are on the white track here. Thank you, Harvard. Okay. Okay, so the color of these dots is only determined by longitude velocity information and not determined by distance or parallax. And so you can see that the longitude velocity information certainly gives you arcs in this plane, give you arcs in this plane, as they should, if we're really mapping spiral structure in the Milky Way. So we've started to get a big piece of this outer arm in the Milky Way mapped. We have lots of sources of what's called the Perseus arm in black here. An interesting thing that happened when we went to do this was we expected to see a fair number of sources in this part of the Perseus arm, which is thought to be one of the dominant spiral arms in the Milky Way. We didn't get any. And what happened is many of the sources we thought would be here ended up in here in what's called the local arm. It's actually been called the local spur, but we're finding it has as much massive star formation going on in this local arm of the Milky Way than the Perseus arm. And so that's been another surprise, that the local arm is really a pretty dominant structure in the Milky Way. The sun is almost right at the edge of this. There are inner arms here. This is what's called the Sagittaria-Carinus arm, and this is called the Crux Scutum arm here. And then we get into the galactic center, where it gets very complicated because of the bar structures, which are not totally well known. And we're working pretty hard on that. We've also been trying to determine what are called the pitch angles of the spirals, which is how open or tight the spiral arms are wound. And we're interestingly getting pitch angles that range from about 7 degrees to about 20 degrees. So quite a variation across the Milky Way. Turns out if you look at other galaxies, you also see things similar to that. So that probably shouldn't have been a surprise. And we've also been finding that the scatter, not due to measurement error, perpendicular to the arm fits, increases linearly with distance from the galactic center. Something we've also just looked at, which no one ever had before, in other galaxies, and we find that happens in other spirals too. Okay, let me just in the last 5 or 10 minutes here go into a little bit of galactic dynamics and how we deal with stuff. As I mentioned, we measure parallax and proper motion. I've only talked about the parallax and sort of treated the proper motion as a nuisance parameter. In reality, it's got lots of very interesting information. So if we measure the apparent motion of, say, a high-mass star-forming region here, in this direction, now we're measuring that in a heliocentric reference frame. If we wanted to go to a galactocentric reference frame here, we have to add back in the motion of the sun. And the sun is thought to move at about, well, the IAU value for the circular rotation speed of the sun, theta naught, is 220 kilometers per second. And it's supposed to have a peculiar motion, a non-circular component that's about 10% as big. So there's sort of those two vectors there. So if you add those two vectors back into our measurement, you transform to a galactocentric frame, and you would get this motion for that cloud. And so we can take that information directly and make a rotation curve for the Milky Way, which is how fast the Milky Way rotates as a function of distance from the galactic center. And so here's our rotation curve for the Milky Way. So it's rotation speed in kilometers per second from about 250 here down to about 150 here. As a function of distance from the galactic center in kiloparsecs, this is 10 kiloparsecs here, so the sun's about here. You can see from this that the rotation curve, at least outside of 4 kiloparsecs, from about here over, is very flat. Very hard to measure actually any slope in that. That's what the dashed red line is. You could try to fit more complicated rotation curves in straight lines, and there's this universal rotation curve for spiral galaxies that actually does a pretty good job of going all the way in toward the galactic center. But we need a lot more data here before we understand what's going on there. And one would not expect to have nice circular rotation for any source near the bar in the galaxy anyway. Okay, this is, you may, if you want to look in the literature, you'll see a lot of rotation curves for the Milky Way. Two things you should know. First of all, they're usually based on one dimension of velocity, just Doppler shift, and they usually are based on pretty poor distance measurements. These are really gold standard results based on, really good distances and 3 dimensions of motions. The other thing you'll notice about most rotation curves is the actual height of this, the speed of rotation, okay, is dependent on the motion of the sun that you put back in. It's highly dependent on that. And so I've put in these two numbers, the distance to the galactic center and the rotation speed of 240 kilometers per second. And in the next slide or two, I'll tell you how we get that. But just sort of beware of rotation curves that usually are based on assuming that number. So how do we get that number? Well, we model all the data. You need all the data together to be able to do it. And basically, we have as independent variables the 3-dimensional positional information we have. And the data that we fit are the 3 dimensions of velocity, the 2 of proper motion, and the Doppler shift. And since we have distance, we can convert the proper motions into linear speeds easily. To model the Milky Way, we're doing the simplest thing we can these days. We sort of give it 3 parameters. The distance to the center of the Milky Way, the rotation speed, and a slope on the rotation curve, which turns out to be a very small number usually. And as I mentioned before, you need to know what the sun is doing the solar peculiar motion, and we can try to measure that. And then there's a possibility that all of our sources, on average, have some systematic motion. Let's say they might all be orbiting a little slower than circular speed, which is sort of a whole nother talk, and I won't get into that. But it's not expected to be very big for high-mass star-forming regions. So we do that, and just to go give you a few numbers here, we put some priors on the solar motion and the average source peculiar motions, very generous priors. For the solar motion, in the direction of galactic rotation, we're putting in 15 plus or minus 10 kilometers per second, which sort of covers all the values that you can find in the literature for this parameter. And we put in that basically the high-mass star-forming regions are moving very slowly with an uncertainty of maybe 10 kilometers per second, which is, again, is a very conservative prior. When we fit all that data, we get 8.34 plus or minus 0.16 kiloparsecs for the distance to the galactic center. So that's a couple percent uncertainty. That's probably the most direct and most accurate distance to the galactic center. For the rotation speed, we get 240 plus or minus 8 kilometers per second. That's significantly above the IAU recommended value. And we get a very small slope on the rotation curve of, a couple tenths a kilometer per second per kiloparsec. That could easily be 0. The rest of the numbers in this table are almost the same, and they depend on different treatments of these priors, and are not very interesting. So, I was going to tell you that there are lots of things that the galactic parameters play into in astrophysics. For example, distances in the galaxy, if you change them, if people use kinematic distances to star-forming regions or gas clouds, those can be significantly in error and systematically in error if you use the wrong constants. That'll change, of course, distance, luminosity, mass, and age of all young objects in the galaxy. If you want to do dynamics in the local group, you want to transform from where we are observing in the sun to the galactic center. And so you have to know those values, especially theta naught, very accurately. And that'll affect things like, is the Large Magellanic Cloud bound or not bound to the Milky Way, and questions like that. But here's kind of a cute example of the impact of these parameters. The effect of R naught and theta naught on whether or not gravitational radiation damping is decreasing the spin period of the Hulse-Taylor binary pulsar. So basically, obviously, if you remember, the spin-down rate has an observed rate for this binary pulsar. You have to correct for galactic accelerations, any galactic accelerations that are going on, and then divide by what you'd expect for GR, and you get a figure of merit for gravitational radiation. And so there are accelerations in the galactic orbit of the sun and the galactic orbit of the pulsar. It's v squared over r, which in this case is theta squared, theta naught squared over r naught for the sun, and theta squared over r squared for the pulsar. So if we use the old IAU values, the current IAU values actually, with accuracies that were known sort of circa 1993 when Hulse-Taylor got the Nobel Prize for this pulsar, the figure of merit parameter was 0.994 with an uncertainty of 0.002. 9994, excuse me. If you use the values that I've just told you are better values for R naught and theta naught with considerably improved uncertainties, the figure of merit becomes 0.9976, and the uncertainty is dropped by a factor of 3. So it's really made a significant difference in this. But you'll notice that this is about a 3 sigma departure now from parameter being 1 for GR being correct. And so the dominant source of error now is the unknown distance to this pulsar. And people had been assuming it was at 9.9 kiloparsecs. If GR is correct, if we force this value to be 1, we can make a prediction that that pulsar will turn out to be at 7.2 plus or minus half a kiloparsec. And so we'll just wait and see. People are now trying to measure this with direct trigonometric parallaxes also with very long baseline interferometry. So I think I'll end there. Thank you.
So we have time for some questions.
So a couple questions. How do you pick your initial set of targets?
Well, basically, there are basically about 1,000 or so masers that are strong enough for us to observe in the northern hemisphere. And we started mostly with those that were strong and had background quasars close to them. And when we're going away from that now as we're going down our list and more targeting certain areas of the Milky Way. For example, let's see if I can get back to a slide here. There we go. So we've been trying to find sources out here in the outer arm, and we've really been working on trying to find some sources here past the galactic center. So we're here, down in this range, to figure out how these arms are curving in here. And then, of course, the next step, which I didn't mention, is we're going to have to do this in the southern hemisphere, which would give us access to this part of the sky here. But there's no shortage of targets.
Mark, what can you tell us about proper motions, in particular SAGB2 that you mentioned with that curvature with the proper motions? What is it? That's a very interesting cloud.
I can't remember the number. It's about 5 milliarc, 6 milliarc seconds a year, and that sort definitely has a. Sorry.
You're going to convert that to kilometers.
Oh boy, it's probably about 100 kilometers per second, but I have to go look up the number. The main thing is it's not terribly circular. We can pretty well see that. So those sources that are within about 3 or 4 kiloparsecs of the galactic center are definitely not on circular orbits, whereas the ones on the outside are pretty close to circular orbits within about 10 kilometers per second.
These measurement velocities, can you get improved estimates of the amount of interior dark matter?
Okay, in other words, use that rotation curve and decompose it into dark matter, disk, and bulge or bar. You ultimately, hopefully, could. I think the correlations are very high between the different components because they don't have that much of a different shape. So you can try to do that. We haven't really tried to do that yet. I think if we can get sources on the backside, maybe we can start to do that. I think what's really needed, if you really knew, for example, the dark matter was an NFW profile or something like that, and could get measurements way out here, even much, much further out, that would constrain that. And then you could separate the disk from the halo a lot easier. But it's not going to be an easy problem.
Any last questions? Okay, we have last question.
You led up to the next question, you said there are 1,000 objects.
Yeah.
So is it potentially just more time, more objects, better models? You can go up to 1,000?
Yeah, sure. We could if they would want to give us that much more time. We've been really blocking out huge quantities of time. It turns out the parallax measurements in the galaxy, really, there are a lot of sources. If this is the sun, there are a lot of sources down here. And then it goes 6 hours away. There are a lot of sources up here. And so we saturate the observing in March, April, and September, October, which is when the peak, that's when the Earth's orbit is elongated the most looking at the source. And so we're taking, almost all the time in that period, huge fraction of the time. So they'll be quite happy to see us go, I think, in a little while. What would we gain? We will double this number in the next year or so when we finish up. At that point, I think it's probably diminishing returns to do another few hundred. The scientific impact might be low. What will be most interesting, and we'll have to probably propose for follow-up work, is if we can get some objects way down here. And those will be hard to do because they're weak, pretty far south, which isn't great for our telescopes. And so they're technically quite challenging.
But the set that you have now, the sampling is such that you're sampling nicely and appropriately the mass in the different arms?
There's no objective way to say we're sampling except that for example, I can tell you there's almost nothing, no high mass star formation going on in that part of the arm. That, it became obvious when we started doing this. We've looked at dust maps and at molecular maps, and indeed the dust quantity goes way down in this arm, in this region here. And so there's really almost no high mass star formation going on. I think we have one source we found in there recently. So the arms are very non-uniform. And our sampling is just basically by strength of the masers, so they're easier to do. Okay.
Thank you.
Turn off Wi-Fi. Next time I will.
Project for the SKA.
Yeah, although we're going to try to. SK is a little bit far off for my lifetime, so we're going to try to do it with some fairly small